All right, how's it going today? Cool. I would like to go over the study guide I posted on Canvas, just sort of talk through that, but also answer any questions you have about the midterm, which is on Friday. And then we'll go back to talking about trees and looking at some algorithms for dealing with trees. So any questions up front? Yeah?
How many problems are we have?
I think I have 3 programming questions and then like 10 or 11 short answer questions.
Is there any overhead cost from doing recursion on a tree instead of iterating?
Yes. So recursion takes more memory. If you had a very deep tree, potentially it could take a lot of memory, but it would have to be really deep. It's probably a little slower because function calls are inherently expensive. But it's easier to write. So yeah, it's a bit of a trade-off. Usually not enough that we worry about it though. Yeah?
For the midterm, is there some unknown reason why if you got a perfect score on the program assignment 2, why your note sheet wouldn't just include you copying word for word program assignment 2? Is there some hidden cost with that? Is that not helpful?
Wait, say it again?
So for the midterm, if you have a perfect VA2 and you're allowed all of your notes, if you copied word for word your coding for VA2, is that a bad strategy or is that a good strategy?
You mean copying it to your notes or using it on the midterm
notes.
or what?
Copying it to your notes for the midterm.
Rewriting it from scratch would be better.
Yeah.
Right? So if you tried to reproduce it from your head with the idea of what a linked list is, right, that's excellent practice. Or in particular, if there were parts of it when you were writing that were particularly troublesome, I kept having trouble when I tried to delete from an empty list, right? Going back and trying to rewrite that from scratch on a board or a piece of paper, that's good practice, good way to nail down the ideas. Yeah. The exam will not include a question such as write a function to add a node to a list. I'm not going to ask you to do that on an exam because you've done that in a PA and you can theoretically bring your programming assignment code with you to the exam. So asking you to do something exactly like what you've already done doesn't really help either of us with assessing. But similar to things you have done for the PAs, you'll be doing things on the test. You've done 224 with me, most of you have, so you know kind of the style of things that I ask in programming questions on tests. Other questions? So I don't think there's any big surprises in here, but just kind of a more or less complete list of what we've been doing so far, right? We've obviously been talking about structures. You should be able to define a structure, struct, variable name, curly bracket, list of field declarations, close curly bracket, semicolon. And you're basically defining a new type of data. And if you want to declare a variable to be that type, you say struct, structure name, variable, semicolon, right? So you're not able to do any of the stuff we've been doing here coding-wise until you can make a structure. So that should be pretty well nailed down. We deal a lot with pointers to structures. That's what we mainly pass around through our functions and come back from functions. And so when you have a struct node star and you want to access the structure, you can just say star variable name. But if you want to access a field in that, you could say star variable name dot field, but we usually say variable name arrow field. And the arrow is a combination of dereferencing and then grabbing a field. Yeah?
So the arrow and the period can be used vice versa in some cases?
More or less, but no. So struct node n, we can say n.data equals 5. Perfectly valid. Okay, struct node star P, P is a pointer to a struct node. P dot data, that's a syntax error.
Okay, so if it's a pointer to a struct node,
Then we'd have to say star P dot data.
what if in, like, for example, PA1, if you were to use arrows instead of the period, would that have worked?
It might, because a pointer and an array are the same thing, but it would work kind of out of luck. Right, it's not something I would do if you're using an array. But if this works, then also this works. Right, that's exactly the same thing as that. And if we said n arrow data, that's a syntax error. So the arrow says dereference and then grab a field. So allocating memory, right, that's the malloc function. When you malloc something, you have to tell it how many bytes to malloc, and we want to do that by using size of and a type of variable, right? Not size of variable name, but size of integer or integer start or struct node or whatever type of variable we're going to assign that memory address to. And structures can be arrays just like anything else. You could have a struct node stuff bracket 10 and you've got an array of 10 struct nodes. So linked lists, the main structure that we've been working with up to this point. So Sentinel nodes, right? You should understand the concept of a sentinel. It's a node that's always present. So if you have an empty list, it still has a sentinel, which means the first node of the actual physical list never changes, never goes away. It's there from the beginning, but it doesn't actually constitute part of the list that we care about. It's just a placeholder that's going to point to the first node when we insert something. So PA1, PA2 is all about searching and inserting and deleting and traversing the list, so you should be familiar with those. Doubly linked list, just throw a back pointer on each node. So when you get to a node, if you want to go to the previous node, you can just follow the back pointer. So 2 nodes pointing on each instead of 2 pointers on each node instead of 1. I didn't list circular list, but we talked about circular list. Basically, at the end, instead of pointing to null, point back to the first node. And now you've just got a big loop of nodes. Keep in mind order of complexity of operations, right? Because that kind of motivates a lot of what we do in this course. If you have an array and you want to add something to the array, if you just add it to the bottom, it takes 1 operation. If your array is sorted, it might take n operations because you have to move stuff around. If your array is sorted, you can search in log n operations because you can play high-low. If your array is not sorted, it's order n to search because you have to check every one of the n elements. So those kinds of things. And with a list, inserting and deleting from a list is order 1, once you know where you want to insert or delete. So if you want to always insert the first node or delete the last node, delete the first node, that's order 1. But finding something in a list is order n, because you've got no choice but to go node by node. We can't play high-low. Trees, which are not part of the midterm, turn the search into order n, or log n, because we can play high-low. Let's see, order of complexity. Okay, so star, ampersand, and arrow. So star says, right, I think you all know this, but if you have any doubt, right, star variable says go to that address in memory, tell me what's stored there. Ampersand variable equals the address where the variable is stored. So if variable is equal to 5, star var is saying the contents of memory location 5. Right? Var is just saying the contents of var, which is 5. Star var is saying the contents of memory location 5. I don't want the value of var. I want you to take the value of var, 5, tell me what's at that address in memory. Ampersand var says I don't want the value of var, I want to know where you stored var in memory. And if var is stored at location 20,000, then ampersand var is 20,000. And they're kind of complementary operations. Pass by value versus reference, as you just remember, we always pass by value in C. So whatever you pass to a function, you can't change that thing in the caller. If I call a function and I pass I, when I get back, I is going to be exactly the same value it was before I called. And that's absolute, right? If I say function I, guaranteed when I come back from this function, I will not have changed value. Never. Okay? Doesn't matter if it's a pointer or a structure or a struct node star or anything. I itself will never change value as a result of calling this function. But if I is a pointer, the thing that it points to can absolutely change value. Right? But I itself is, we don't actually pass I. We just take the value of I and we pass that. But if you say something like I equals address of X, and then you say function I, my function might say, let's take the thing that I points to, that's X, and let's set that equal to 0. And when I come back, X will have changed to a 0. But the I itself that we pass to our function is just some number that's the location where X is stored. So that's the long-winded notion of pass by value. Pass by reference would mean that we were actually just passing, if we said function I, we'd actually pass the address of I automatically. And some languages do that, like Pascal. Malloc and free, you've been using those. Malloc allocates a block. Free, you pass it an address that you got from malloc. Right? You can't just free an arbitrary memory location. You can only free something that malloc gave you, and it will release that memory so that something else can use it. And Velgrind is your handy dandy tool for looking for memory leaks. So it keeps track of every time you do a malloc, every time you do a free, and it tells you how you did at the end as far as house cleaning. GDB, more of you are using GDB now, which is great. It's definitely helpful. So you should know the basics, right? Put in a -G switch to compile a program with GDB support. GDB executable program to run the debugger, and then start to begin. Break followed by a function name or line number to say set a breakpoint. Continue to say run until you hit a breakpoint. Next to say execute one line of my program. Step to say execute one step, which means if my current instruction is a function call, go into my function and stop. So you can single step with next and step. Print the value of a variable X to examine a memory location. And that's kind of 95% of what you need for GDB. Watch variable name if you want a watch point. You did that on the GDB quiz, but that's kind of it. So just sort of the basics. Make files. Most of you like make files. Some of you are not close friends with make files yet. Grab a make file from your notes, right? Or from something that we posted, and mess around with it, right? Basic idea, if you got a make file, you say make and it builds your program for you. The make file is the recipe for doing that. It's the set of conditions that have to be satisfied and the things you do if those conditions are satisfied to create a make file. If that's not clicking for you, right, post a question on Canvas. make yourself a make file, and if it's not working, go ahead and post it in the discussion area and say, here's my make file, here's what it does when I run it, you know, copy and paste the output, and let's just talk about it, okay, before Friday. And really, once you have a make file that works, you can just modulate it to make files for future projects. But it will help you keep yourself productive. Abstract data types. So anytime we talk about data structures in this course or any course, we should always understand what this structure looks like from an abstract point of view. So we have to do this with trees today. If we ignore the details of how we're going to write the code to implement the structure, what does the structure look like to a user? So for a list, what do? We initialize, we insert, we search, we delete, we traverse maybe, we release the list. That's probably it. And we might do that with an array, we might do it with a bunch of struct node pointers, we might do it with, you know, whatever. But those details are under the hood, right? We want to know, what does it look like to the user? Well, I call insert and it inserts something and it puts it in increasing order. I don't care how it does that, right? Do I start at the beginning and go through? Do I leapfrog back and forth? I don't know. When we get to Java, you know, we'll play with lists and we won't even know if they're actually lists. They might be something else that's more efficient, or hashes or things like that. But to us, it looks like this abstract data type, and we have these functions for interacting with it, and this is how these functions are guaranteed to behave, and that's all we know about it, right? So keep in mind abstract data types. So stacks and queues, I'm not going to ask you to do any coding with those, okay? But you should know the concept. So stack is a last in, first out. You add something to the stack right here. If you say pop something off the stack, that's the thing you're going to pop, the thing you just pushed. If you push 55 things and the last thing you pushed is right here and you say pop, that last thing you pushed, that's what you're going to pop. Doesn't matter that you pushed 55 other things first. The last thing that you push, that's the first thing you pop. Okay, stack of dishes at the buffet, last one you put on top, first one you take off. Queue is first in, first out. Okay, think checkout line. Somebody comes into the queue and 55 other people come in. The first person to come out of the queue is the first one who went in. 1,000 people might stack up behind, but when they open the doors at the concert, first person in is the first one who was in line. And the 1,000th person who came into line, they're the 1,000th person who's going to come out the other side and get into the concert. So first in, first out is a queue. Yeah.
For the keyword, like I looked it up, they have different keywords for like the queue thing.
What kind of keywords?
Like they have the default, but for the remove they have like a DQ or something.
Yeah,
like
so
that.
removing is sometimes called dequeuing. Same thing.
Oh, okay.
And it's more common to insert at the tail and remove from the head, but some places use the opposite terminology. So I'm trying to be completely consistent. Insert at the tail, remove from the head. Okay. Anatomically backwards, if you like. And removing, dequeuing, same thing. Insert, add, same thing, right? But you're adding something to the queue always happens at the tail. Taking something out of the queue always happens at the head for us. And queue can be empty if there's nothing in there. Queue can be full if you run out of places to store things. Stack, same thing. If you've got no space left and you try to add something more, that's an overflow. If you try to remove something but there's nothing in the stack, that's an underflow. I did not put hashes on here. Hashes should be on here. You should know the concept of a hash. So a hash is a way to take a key and map it to an index in an array typically to tell you where you should store this key in the array. And we usually have a key and a data pair, and we might have parallel arrays, or we might have an array of structures or something, but the main characteristic of a hash is that you take the key and this thing called a hash function or a hash map changes the key into an index and says, okay, here's this key, this is going to go at index 7. And then when you want to look for this key later, you don't have to search every location in your array. You do the hash function and it says this should be stored at location 7. You just go straight to location 7 in your array and look for your key. And so theoretically it's an order 1, a fixed amount of time. Other than when you start getting into collisions and all of these details. Okay, but I want you to know the main concept, right? Take a key, map it to an index. All right, and then things you should be prepared to do. So the programming questions, right, you'll basically be writing code to do something with a data structure, probably linked lists. And you'll have to dereference pointers, you'll have to use arrows, stuff like that. So things you've done in your PAs, basically. I might give you some code and ask you what it does. I might give you some code and ask you to make changes to it. Discuss performance of algorithms. No, I'm not going to have you discuss it, but there might be like a short answer, multiple choice kind of question. So you're not going to write an essay on order of complexity of linked lists. Understand and be able to perform operations on lists, stacks, and queues. And short answer questions or multiple choice on GDB, Valgrind, make files, hash functions, things like that. Shouldn't be any surprises. Yeah?
The performance of algorithms, is that like the log n?
Yeah, that's like inserting into a unordered array takes one operation, it's order 1. If it's sorted, it takes order n, that kind of thing.
Are you going to throw anything at us that we haven't seen with that? Like, are we going to have to calculate, is this log n minus 1 or anything?
No, I'm not going to ask you to do any analysis of performance. I just want you to know general concepts.
Can you give one example?
One example? Let's see. I don't know, true or false, inserting into a sorted array takes the same amount of time as an unsorted array, right? And that's false. If your array is sorted and you want to insert into it, you might have to move everything down because, you know, you've got to put something in the middle here. There's no space for it. If it's unsorted, you can just insert at the bottom of the array, right? So inserting into an unsorted array is probably faster than a sorted one. So, but that's not a question on that. Yeah.
Kind of on the program assignments, is there any kind of code, like coding we should review from 224, or is it pretty much what we've been doing in the PAs?
I'm not going to ask you stuff that depends on command line arguments or scanf or things like that. But if there's anything that you're really not comfortable with, like, I don't know, you know, how to return a value from a function or something like that, that's kind of a 224 thing. Make sure you're okay with that. But
Yeah.
everything you might see on the exam, you've probably already dealt with in the programming assignments for this course.
Oh,
So.
yeah. I just wanted to make sure there isn't some weird thing.
Now, I'm not going to bring back some weird.
Mainly it was like the scanf stuff. You're gonna have
Yeah, I'm not gonna hit you with that. I'm not gonna hit you with fopen or fork or any of those 224-ish things. But they're good to know anyway.
Well, I know it's just not like, you know,
Yeah.
remember things.
Yeah. All right. Any other other questions? All right. Back to trees. So yeah, let's look at trees as an abstract data type. Let's think about what kinds of things we want to do with trees, and then we'll start developing some of the algorithms abstractly. Some kind of initialization. But initializing a tree is going to turn out to be really, really, really easy. We're really just going to set the tree equal to null, and that's going to represent an empty tree. So we're not really going to need an initialized function. We're going to want to insert some sort of data into a tree. And we're thinking binary search trees here. So insert needs to insert in a way that preserves this ordering on the data, so that when we traverse it in order, we get our data out in order. So we want to insert. We want to be able to search a tree for some data. We probably want to be able to delete a piece of data from a tree. And let's just say print. And print is not a terribly useful function, because we don't always want to print. Probably what we want to do is somehow traverse the data in this tree. So we can say, okay, every time I call this function, I want a new node from this tree, and I want to get these nodes in order. But for us, I'm just going to say print. So print t is just going to print out the nodes in order with like spaces between them or something like that. But this should probably be some sort of traversal function. And we could say release, which should delete all the nodes in the tree and return all the memory the tree is using back into the pool of available memory. And you'll do this at the end of PA4 so you don't have memory leaks. I'm not sure we need anything else here. Insert, search, delete, traverse. That's a pretty good collection, but we might also have something like height. We give it a tree and it tells us what the height of the tree is. And remember, the height is the depth of the deepest node, and the depth of a node is the number of links from the root to that node, number of steps you have to take. So it might be nice to have a function that tells us the height. So let's think about height for a minute. We've got a tree. And we want to find the height of this tree. And we can look at it, because we've got these marvelous brains in our head and our optic system. We can look at this and we can say, let's see, 1, 2, 3, 4, 5, 6, 7. Height of the tree is 7. How in the heck would we get a program to do that? the height of the tree is the depth of the deepest node. So if we could find the depth of every node, and as we calculate each depth, we compare it to our deepest node we've seen so far, and keep track of whatever is the deepest, at some point we'll find this node with a depth of 7. And when we finish checking the depth of every node, we could say the height of this tree is 7. And how do we check the depth of a node? Well, we start from the root and we travel down until we get to that node. So if we're looking for the depth of this node, we'd say 1, 2, 3, 4. Oh, this is a depth of 4. But we need to do that for every single node. And that's a tricky prospect. That's a traversal question. Because we start here, well, should we go left or right? The answer is we have to do both. So first we'll go left, and here's another place we have to decide, do we go left or right? Well, we have to do both. So first go left. And here we can only go right, and here we can go left or right. So first we'll go left, and if we've kept track of everything, we'll decide this has a depth of 4. And then we'll go right, and this has a depth of 4. And this has a depth of 3. But then we have to come back here, and we have to go off to the right. And there could be other stuff hanging off here. And so we're back to this traversal question, and we can do this by using a stack to keep track of all these decision points. Or we could try to write a recursive traversal function. And as we go through, every time we get to a leaf, record the depth of that node. But if we think lazy, if we think I don't want to do that much work, let's find a better solution. We can come up with a recursive height function. And a recursive height function is based on the following observation. Here's our tree T. It's comprised of two subtrees, T dot left and T dot right. If I could find the height of these two trees, whichever one has a bigger height, if I add 1 to that, that'll give me the height of T. So the height of T is 1 plus the largest of the height of the left subtree or the height of the right subtree. And that sentence right there translates to one line of C code. So let's take a tree and let's find its height. And I'm assuming we have a max function which gives us the largest of two arguments. So 1 plus the maximum of height of T dot left and height of T dot right. So if you want the height of T, take the left subtree, find its height. Take the right subtree, find its height. Pick the largest of those two, add 1, that's the height of T. Does that make sense? Now there's one detail we have to add here. Anytime you have recursion, think about a base case. Because when we ask for the height of T, it's going to call height, and when we call that height, it's going to call height, and it's going to keep calling height again and again and again. When is that going to stop? And if this is all I have in my function, this call is never going to end. It's going to keep calling height on smaller and smaller subtrees. So to find the height of this subtree, it's going to look for the height of this and the height of that. And to find the height of this, it's going to try to find the height of this. And to find the height of those two nodes, it's going to ask for the height of the single node. And to find the height of that single node, it's going to try to find the height of its left subtree, which is null, and its right subtree, which is null. And if I call my height function with T equal null, this will generate a seg fault. But if my tree is null, I don't need to find the height of the subtrees to find the height of T, because I know that if T is null, what's the height of a null tree? -1, special case. So there's a complete height function. And it's basically a base case and a recursive step. And this will work beautifully. Suppose my tree consists of a single node, just a root. And I call height. Well, it says if t is null. Nope, it's not null. It's actually one node. So let's find the height of t dot left, which is null, and the height of t dot right, which is null. Well, when I call the height of null, I'm going to get back -1. And when I call height over here, which is null, I'm going to get -1. So this is going to return 1 plus the maximum of -1 minus 1, which is -1, which is 0. So my height function is going to tell me the height of this tree is 0, which is exactly correct. Because if you only have a root, the depth of the root is 0. And you can work your way up and see examples where this will work. But if we think of conceptually what this is saying, right, it's find the largest subtree, take its height, add 1 more for the root, that's the height of the tree. And this is typical of what we're going to see with all our algorithms with trees. The recursive versions are going to be really, really short, mostly. At some point, the iterative ones will be just completely ridiculous, and we won't even want to think about them. And we generally won't code them up. Iteratively, we'll almost always use recursion. This is one reason why we don't want sentinel nodes, though. Because if our tree T had a sentinel node, if we had some sort of, magic sentinel node up here, then when we took the left subtree, we'd have this thing, it wouldn't have a sentinel node anymore. And when we take the right subtree, it wouldn't have a sentinel. And we'd need to sort of artificially create one, or think of this as a sentinel or something like that. And it's going to mess up the recursion. We really want every piece of this structure to look like the original structure itself. So let's look at lists for a moment again. So let's look at a linked list with no sentinel. So we've got a list, and this points to whatever the first node of our list is, or list is null if there's no nodes. Well, let's write a print function for our list. Something that goes through and prints the value of every node in the list. And if we want to be, we know how to do this. We can have a pointer and we can move the pointer down until it's null and so on and so forth, right? But if you really want to be lazy, if someone hands you a list and says, hey, can you write out on this piece of paper, everything that's in this list, what's the really laziest way that you could do this other than just handing the whole list to a friend and say, can you write out this list, right? You could just look at this first number and write that down on a piece of paper, and then take the rest of the list, hand that to a friend, and say, can you print out this list for me? And they'll say, yeah, it's this, and you've got the first number already written down, and you're done. And how does your friend print out this list? Well, they're going to print out the value of the first node, and then they're going to take the rest of the list and hand that to another friend and say, can you print this list for me? And each time this happens, the list that's being handed to a friend is smaller and smaller. Until eventually, somebody has a list with a single node, they print out that value, and they hand their friend an empty list. and say, can you print this list for me? And the friend says, that's empty, here you go. I don't have to do anything. So what does this look like if we code it? So here's print list. If the list is null, return. Otherwise, let's print the data in the first node. So we'll use a printf statement. And then we'll say print list arrow next. And there's a perfectly good print function. And it's recursive because for print to work we have to call print. Let me call this my print so it doesn't look too much like printf. For my print to work it has to call my print. Right? But the code is trivial. If the list is empty, do nothing. Otherwise, print the first node's data, and then print the rest of the list. Yeah.
And if the list is big enough, we wouldn't run into memory issues?
Oh, if it's big enough, you'll run out of memory. Because recursion uses more and more resources each time that you recurse. Because you got to remember everything about where you were. So this would not be something you would typically do unless there was a good reason to. Because if your list had 1 million nodes, you'd be recursing 1 million times. That's probably enough to blow up some machines. But with trees, the amount of recursion is usually based on the height of the tree. And a tree with a height of 1 million would have 2 to the millionth things in it, theoretically. And that's never going to happen, practically speaking, especially if it's a balanced tree. So 1 million things would be a tree of a height 20. So that's not a lot of recursion. So let's write a search function. It's linked list, no Sentinel node. We want to search a list for a number. If the list doesn't have anything in it, then it certainly doesn't have our number in it, so we return 0. So that's our first case. If the list is empty, your number is not in it. If the first node happens to have the number we're looking for, we're done. We found your number. We return a 1. If the list is not empty, but the first node is not the number you're looking for, we don't know if the number is in the list or not. It could be somewhere in the rest of the list, right? And we've done enough work, so we'll ask a friend to search the rest of the list. And whatever our friend tells us, that's what we're going to tell the person who called us. So we're going to say search the rest of the list for the number, and whatever value we get back from search, that's the value we return. And there's a 3-line search function. So we could do an insert function recursively also. How would that work? If the list is empty, add the number to the end of the list. If the first number in the list is bigger than what we're inserting, make a new node, turn that into the beginning of the list. Otherwise, we can say insert my number into list arrow next. Right? Just pass the insert function the remainder of the list and say put it in the right spot in here. So a lot of times we can take these functions that we think of iteratively and rethink them to be recursive. And it's not an entirely natural way to do things, but it can become more natural. And it's a really powerful approach to algorithms. So there's some examples with lists. Like I say, we don't normally do this with lists because lists, the iteration is just about as easy as the recursion, because our recursive call is at the end of our function. So this is what we call tail recursion. Tail recursion, easy to turn into a loop. Recursion in the middle of stuff is a little harder, but you can do recursion, you can fake recursion with loops, right? You just have to remember where you were, so use some kind of stack structure, and you can just keep branching and pretend you're doing recursive calls. So even languages that don't support recursion, you can do these recursive things. All right, let's take a really quick look on insertion. So somebody pick a number.
55.
55? Okay, so let's insert 55 into this tree. So iteratively, right, we start at the root. Should 55 go to the left or the right of the root? 55 bigger than 40, you got to go to the right. All right, should it go to the left or the right of 60? Should it go to the left or the right of 50? Is there anything to the right? Nope, that's where we're going to put our 55. We're done. It's that straightforward. All right, give me another number. 12. So smaller than 40, smaller than 20, bigger than 10, nothing there. There's our 12. So insert, we just start at the root, we move down, going either left or right based on whether a number is smaller or bigger than the current node, until we get to a spot where there's an empty space, a null that we can put our number. That's where we put our number. Yeah?
Try 65.
65. All right, go to the right, go to the right, go to the left, nothing on the left, 65.
Try 40.
40. So we're going to imagine that you're not allowed to insert something that's already in the tree. So otherwise you got to have some rule for where should that go. And if you did that, it would have to go, you know, probably down here at the 30 or maybe to the left of the 50. But then it gets weird. So yeah, we'll assume when we're talking about trees, you can't have something in there more than once.
At any point, are we going to have it so that it restacks the tree, so it's always...
Oh yeah. Yeah, so this can get you really unbalanced. So we'll talk about that tomorrow.
Yeah, like when we go to 55, it's between 50 and 70. So what if you saying the right side of 54, left side of 70?
It can't go on the left side of 70 because it's got to be bigger than the root. Right, so everything to the right of 60 has to be bigger than 60. So 55 is smaller, you got to come to the left. So really the only place for it in this tree would be right there. Say what? Not just smaller, no, but yeah, 55 is bigger than 50, so it goes to the right.
It's also smaller than 70.
Yeah, but you don't actually get to 70, right? When you get to this node, you're forced to go left because it's smaller than 60. So you're not even considering this tree.
But we could have something like 61 or 65, like the right side.
If you had 61, you'd get here, you'd have to go to the right. 70, you'd have to go left. That would be your 61.